me start that. My music. Okay. So today we will go over the answers to assignment 1. I'd like to make sure that if you have been granted an extension to this assignment, please do not view the lecture until your assignment is submitted. Feel free to return at 1 p.m. to rejoin this session after the answers are discussed if you want to learn a little bit about or want to ask some questions or continue kind of getting help with your extended submission, or if you have questions about the next block. But at this point, I'm going to scan through the attendees, and if you are someone I have on my list of people that has gotten extended, I'm going to boot you out. No? Not seeing it. Okay, cool, great, wonderful. Okay, so I think like I've been advising you, many of you will probably find today's answer session a little frustrating because the answers are probably simpler than what you anticipated. I'm sorry. I've tried really hard for the next assignment to give you as much scaffolding as possible without kind of removing the problem-solving nature of the assessment. So you can thank Tom and Lenka for their feedback to make sure that the kind of cliffs have been smoothed a little bit while still retaining a significant amount of problem-solving content. So moving straight forward to doing data science mentally. The whole point of this section here is to try and get you to get used to doing conditional expectations. And remember, from our lectures and from the workbook, all a conditional expectation is guess about Y when we know something about X. So it's a guess about the price of a house when we know something possibly about its properties, about what year it was sold in, how many bedrooms it has, et cetera, et cetera. So I would suggest that you read in the data in library tidyverse just like this. Some of you may have seen in my notes from last assignment that if you library tidyverse, you shouldn't need to library all the other packages that are within tidyverse. Part of this was kind of catching if you realized this from the last assignment. So I just want to make sure that you know that tidyverse contains a bunch of packages, and you shouldn't need to library all of them independently once you library tidyverse. So going down to the conditional probabilities, the first question asked, in 1999, what's your best guess as to the price of the house? And I think some students may have also seen the version that said from 1999. I meant it as in, and I clarified that a couple of times in the class, but if you did, so this is the best answer here. And because of my own kind of imprecision in the language, if you did greater than or equal to, I'll give you credit. That's my fault for not being clear. My intent was to say the house is from 1999, or the house sale is from 1999. A listing in this context is like a description of a house being sold, and that has a particular location in space and time. So my thought was that when I said a listing from 1999, that would make sense. But if I said something like a listing from 1999 onwards, then it would suggest that I'm looking for the range. So just to be clear, I've made it in and uploaded it, but it could be that that change didn't propagate or something. So some people have the version that says from. I'm sorry if you got confused by that. But all you're supposed to do here is construct the filter for year equal to 1999, and then summarize it by getting the mean price. And that is a pretty good guess for the price of a house in 1999 if you know nothing else about the price. You could have been fancy and given me the median. That's okay too. Not obviously median 1999, median price. That's fine. Just give me a guess. I'm using the mean because your models are going to be using the mean, but you can use the median. That's okay. Cool. So that's just straight from the last assignment. If you're a detached house in 1999, what's your best guess as to the price of that house? Okay. So if we're in 1999, so that tells you, okay, I need to do a filter that gives me years in 1999. And then I need a filter that is detached house. So I put the and symbol and do my second filter. So this means the thing on the left has to be true, and the thing on the right has to be true. Another way you could have done this is using two filters, where you filter to select the things only in 1999, and then you filter to select things that are property type equals detached among that pre-filtered set. Either way you want to do it is fine, I don't care. I prefer the and because it's more explicit about what you're doing, but the two filters is fine. I think that this works. Yeah. So you can do two filters in that manner as well. As long as your answer gives us the average price or the median price, don't care what you pick, among this group, and you have selected this group in the manner that is accurate, then that should work. So that's all I'm asking for there. The reason why I prefer using and rather than comma is because if I wanted an or condition, I would use a vertical pipe here, this kind of vertical line which is above the enter key on your keyboard. Or maybe it isn't, I can't tell if I'm on a UK. Yeah, I'm on a US. I don't know where it is on the UK. But this vertical line symbol means or in R. So if I wanted to say, you know, property type is 1990 or property type is detached or the year is 1999, I'd use this vertical pipe. Whereas and makes it clear that I'm doing both of them at the same time. When you're using a comma, it's an implicit and. So it's just as many characters to type the and symbol. I guess maybe one more space, but it's just a little bit more explicit. So it's fine if you did it either way. Cool, so that's what I'm looking for here. If it's a flat, is it likely to be sold as a freehold or a leasehold? So here I'm looking for a filter. So condition on the property type, tell me among flats, is it a freehold or a leasehold? So what I was looking for was a filter and a group by, because I want to know what the relative balance is of the freeholds and leaseholds among property type equals flat. If you did this in sort of two different chunks of code that each did a filter, like a double filter where the property type was flat and is freehold is true, and then property type is flat and is freehold is false, that's okay, but it's not the best answer. So the recognition here is that we're looking for a summary over all of the kinds of is freehold and is leasehold. Patrick asks, I did a cross tabulation for 13 and 14. Is that all right? Yeah, it's super okay. As long as it gives you something that looks like the first two columns here of false and true count for each of them, that's great. So if you use a cross tabulation, that's exactly what I'm looking for. And the xtabs function is fine. Cool, does everybody get this? If it's a detached house, is it likely to be sold as a freehold or a leasehold? Is the percent an extra thing? I mean, I just did it just in case you decided to do the percentage rather than the count. Yeah, Willa, the probability is this, I think, is the same as the percentage that you're referring to, so that's fine. And I'm not going to mark you down or up for doing that. So he asked, could you also use summarize for leasehold is equal to mean of is freehold equals 0? Yeah, you totally can do that. That's exactly correct. You don't actually need to do that necessarily. If that would give you the percentage of houses that are sold, but yeah, that works. That's fine to do. Awesome. So the detached house, is it likely to be sold as a freehold or a leasehold? Okay, so just like before, I'm looking for a filter based on a property type and then a group by. So this code should be basically identical to section 1.3. And I'm just asking you to repeat it for a different property type. Now, the enterprising among you might have realized, okay, if I'm doing it for those, why not just do it for everybody? And that would look something like this, where I do a double group by and no filter. If you did this, you'd get an error because property type is not in sales. So this is fine because this gives you the property type detached is freehold breakdown, property type is flat is freehold breakdown, etc. for all the types. Yeah, it is. I'm just doing that to make things clearer in the table. Otherwise, it would be nice and wide. But yeah, I'm rounding it by 2. Yep. So this is a double group by, right? I am trying to get the number of observations or the percentage of those observations that is inside of these groups. So if I group it twice by property type and then freehold, and I do a reduction, I'm going to get the unique summary of everything of the unique combination of the types of properties and the values of his freehold. So I'm going to get a data frame as a result that has detached false, detached true, flat, false, flat, true. Anytime you do a group by, you're going to get a unique combination of all the values that are in each grouped variable. I'm using the count function in my summarize, so I get a column that is the count of the rows in the original data that fall in this unique combination of my groupers. So to show that again there, I'm using the count function to get, oh wait, nope, this is too far, sorry, there. I'm using the count function to get the unique or to get the number of rows that are in each unique combination of the grouped variables. And then finally, I'm using the mutate while the data is still grouped over property type to compute the percentages in each of the property type chunks. So remember, the way that to think about a group by is that it splits your data into individual data frames that have a single value for the variable in the group by. So I'm splitting the data frame into 4 data frames that only have one value for property type. And then I'm splitting each of those again into the trues and the falses. When I summarize it, I collapse that level of grouping. So summarize takes the rightmost level and computes some kind of summary but then I'm still grouped by property type. So if I do anything to my data frame after that, it's referring to the chunks of the data frame that all have the same property type. So when I do count divided by the sum of the count, that's computed for each property type. And that's because I've only unpacked one level through the summarize. So group by stacks things left to right, and summarize unstacks things right to left. You didn't have to do this, but some of you may have recognized that, and you might have done that. So I just wanted to show what that looks like. Cool. If a listing is sold for more than £500,000, is it likely to be sold as a freehold or leasehold? So you could filter, you could group by, and then summarize, just like before. Okay, so that's section one. Just, you've done that exact kind of stuff before. You've seen all that. And the reason why I'm doing this, I'm never just asking you to do this mechanically. It has a point. Later on, we're going to use the exploratory results to kind of demonstrate intuition about your model. So I'm never asking you just to compute something because I find it interesting. If you found out the percentage manually, would you lose marks as it's not tidy? I don't know what you mean by manually. If you mean like you didn't use the tidy methods that I've taught you and you used, say, you built a mask for things that are above that price, and then you maybe took the mean of his freehold, that's not using the pattern that I've shown you. So I'm reluctant to give that as good of credit as something that does demonstrate mastery of the stuff that I've shown you. So the point is, show me that you get what I've been talking about. So getting the right answer is usually good enough for a 2-2 or a 2-1. But reaching into the first, you need to show me that you're actually engaging with the taught primitives that I've done. So if that makes sense, I hope that's clear. Okay, yeah, then that's fine. You don't have to make a new column with mutate. So yeah, it's fine to not create a new column with mutate. It's totally okay. Okay. Yeah, that's okay. I mean, it's not ideal, but it's okay. The main point is the count. I don't really care if you did something other than that. As long as you get the count and you can get the right conclusion from that, I'm fine. It's cool. Okay, next part. Fit a linear model that predicts listing price using a unique mean in each year. Okay. A lot of people had questions about this. And I think it's because some of you read the data in and year already was a factor. And others of you read the data in and it was not a factor. And it was confusing to many people to try and figure out what to do. So when I'm talking about unique means, I'm talking about treating year as a categorical variable, where you get each year as its own effect. Okay? Now you can do a contrast model, or you can do a fixed effect model in this manner, and I don't mind. Whatever you want to do, you need to be able to explain the statistical significance, but you can do either one. Okay? So I'm going to talk about the contrast model for the next question, and then I'm going to talk about the fixed effect model for the next question. Which years are not statistically significant in the contrast model? Why might this be the case? Well, the contrast model is generating its effects for all of the years after the first as the sort of relative impact of being in that year versus in the first year. Just like a typical linear regression, it's the effect of moving into that year from the default year. And because the contrast model contrast model is the one without the +0, yes. Contrast model has an intercept and then the rest of the years. So, if you fit the contrast model, you need to be able to understand and explain that the years that are close to the first year, 1996, 1997, 1998, are more similar to that first year. Therefore, their contrast effects are not going to be statistically significant. But as inflation happens and prices get much larger, those will be significantly different from 0. Because the contrast effect is just for the difference for that year relative to the intercept. The intercept has taken away the baseline, and now all of those things are significant if they're larger or smaller than 0. So the early years are similar to the intercept. So their estimates are small relative to their standard error. The later years are dissimilar from the intercept, which is the first year. So because they're dissimilar from the reference category, they will be statistically significant. If you had a data set of, say, just 95 to 2000, would the contrast effect be greater to the closer years? Generally speaking, data has what's called temporal regressive structure. So basically, years that are close together are more similar than years that are further away. But imagine if we had, say, started our model in 2007, and we had 2007 to 2010, or 2015, let's say. 2007 would be our reference category. 2008, 2009, 2010 had sharp drops because of the housing crisis and the global financial crisis. So all of those might be statistically significant and negative. Then later, when things recovered, we got back up to the 2007 levels. Those years that would be similar to 2007 would not be statistically significant. So the whole point of this is just to try and identify if you can tell what the contrast effects mean and when they might be statistically significant. In this example, the years that are similar to 1995 are going to be statistically significant. Georgia, the contrast model constructs an effect for each year. And that effect is the relative change for that year from the intercept. So this effect for 1996 is the change in prices when going from 1995 to 1996. This is the change in prices when going from 1995 to 1997. This is the change in prices when going from 1995 to 1998. What I'm suggesting is, when you're in 1995, your house prices are at some level, say 70,000 as your average. When you're in 1996, they're still about 70,000. When you're in 1997, they're still about 70,000. But as you go further, say 2004, your house prices are now about 180,000. That is significantly different from our starting point of 70,000 in 1995. So the first years are more similar to the reference category than the later years. That's because house prices in 1996 are probably similar to house prices in 1995. House prices in 2006 are not. Does that make sense? Awesome. Now, if we look at the fixed effect, as some of you did, that's fine. You'll get this result. You have the same effect for 1995 as the estimate, but now 1996 is estimated as its mean instead of being estimated relative to 1995. Okay. You'll see that all of the effects are statistically significant. Okay. Why? Well, the statistical test in this case, just like before, is whether or not the estimate is 0. Does our confidence interval overlap 0? Or is 0 within 2 standard deviations? Or standard errors, sorry. In the fixed effect model, each of our estimates is the mean for that group. Conditional mean for that group sometimes if you have extra variance. So is the average house price in 1996 0? No, it's not. It's really highly unlikely that the average house price is ever 0. The average house price in 1996 is $67,000. Now, that's pretty similar to the average house price in 1995, but it's definitely not 0. So the fixed effect model has all of the effects to be significant because they're comparing the value to 0, not to the first year. And if an effect were statistically insignificant in the fixed effect model, it would mean that group was approximately 0. You couldn't tell it apart from 0. And I don't know about you, but there's probably never a situation in the West of England Combined Authority where house prices are approximately 0, or I couldn't tell whether or not a house was close to 0 or not. Pretty sure people always pay a non-zero amount to buy a house. You and me both, Patrick. That is true. Does that make sense? That's what I'm looking for in this question. Regardless of which model you fit, I want you to be able to explain the pattern of significance in the estimates. I told you that this was a lot more interpretation heavy as we go forward. The code that you're required to write is very short. This was 2 lines. Okay, to 2.1, that's that answer. 2.2, what is the model's prediction of listing price in 1999? How does this compare to your guess from section 1? Okay, there's 2 ways you can do this and they're both okay. One way that's explicit and works for any form of the model that you want is to use your price model and then specify the scenario you want to predict. So this would be, if you want it even simpler, you could say scenario is equal to data frame, year equals 1999, and then predict scenario. That's your prediction. Why do I use C? Just because it's a force of habit. It should be okay to just use that if you only have one element. Yeah. C is like the R language. You've seen that before for sure. It's the R language way of saying I'm going to have a collection of elements, and it might be longer than 1, but it could also be 1. So when I write C, I'm just saying because I've trained my fingers to basically do that every time I'm writing a list of values, even when the list is 1. So it's just muscle memory. You can also do that. So the prediction for the house price is 90,000 in 1999. By the way, if we go back to our solution in 1.1, what's our prediction? The same value, 90,000. So the model is like before in the workbook, just constructing a conditional expectation. Same thing, approximately. The other way that you could do it is if you fit the fixed effect model, as we did here, see, 0 plus as factor year. Look at the 1999 effect. That is about 90,000. But you can only get that from the fixed effect model. If we had a contrast model, you'd have to add the 1995 intercept to the contrast for 1999. And in that case, it's just easier to use the predict function, I think. Did everybody get that? Any questions on how to construct that prediction? Cool. Are there any issues you can detect with your model? Yes, there are. The model is very heteroscedastic and has biased predictions for each local authority. For instance, you could find different issues and you could tell me about them, and if they have empirical support, that's fine. These are the two that I wanted to find. Emily, there shouldn't be any significant difference between using as factor and factor. Those should be both equivalent and work the same. So the first thing that I wanted to see was the heteroscedasticity. And one thing that's really clear in the model is that our residuals get larger as the years go on. So the variance of our residuals in 1995 is way smaller than the variance of our residuals in, say, 2005 or 2015. You can kind of tell that this is going to happen if you look at the box plot we made last chunk. So the box plot we made last chunk is not exactly the same data, but it shows you that there's kind of an increasing variance in the distribution of house prices in the west of England as you go on in time. This is generally the case for all price data. Variance increases and the magnitude becomes larger. So there we go. Does everybody see this? So that's one way you can diagnose heteroscedasticity. You could have also plotted the fit versus the residual. That plot is equivalent to this plot in some ways. The fitted value for each year is just the mean of that year. So if you made a plot of the residual on the y and the fitted value on the x, you're going to be plotting it while shuffling the years around, depending on where they are, but you're still going to have something that looks like this. All of the predictions in a single year will be distributed around that mean. Does that make sense to folks? Do people want to see that? Let's just do that. Instead of me telling you, let's do it. Okay, so group year, GM box plot. We'll keep that and we'll just do group is equal to fit. We'll say X is fit. And we'll do, instead of the box plot, do GM point. So some of you might have made a plot that looks like this. Hopefully not like that, like that. So as I suggested, this is substantially similar to the other one. You can see that as prices get bigger, which is in this case a proxy for time going on, our variance increases. Okay? So as long as you're able to identify that heteroscedasticity exists, that's okay. You could have used a Brush-Pagan test. That would be excellent. If you remember that that's a statistical test for heteroscedasticity, that's wonderful. This is the simplest visual check that you could do to get the right answer. Sound good? I'm going to put this back the way it was. Yeah. So the fitted values plot was fit there, and you don't need the group for that. But it's just a ggplot there. I highly suggest that when you're working with a model like this, you make new columns for the fitted values and residuals in your original data so that you can make the plots yourself rather than relying on the R built-in plots. It's nice when you can use them all in ggplot. Making like the Cook's distance plot is somewhat harder, but there's probably things out there that do that for you already in ggplot. So yeah. Sound good? Folks see it? Cool. As you see here, the driving issue is that the actual variance of sales prices increases each year. So if you take the mean of that year, the variance around that mean is going to increase as you go through time. We're only using the years to allow the mean to change, but the model still assumes that each year's variance is the same. This is the cause of heteroscedasticity. We're assuming that all the years have the same variance when in fact they don't. Now the second part, I'm just showing you another thing. This is the standard deviation in, what was it, prices? Yeah, the standard deviation in prices over years. This is a great way to detect if your model is going to have any heteroscedasticity, especially if you're just using information about years. It'll take care of the fact that price generally increases over the span. It won't take care of the fact that price is increasing in variability. Cool. I do some stuff that shows you, if you want to do a transform, you can take care of it. If you take the log of prices, then this becomes rather stable. But moving to bias, this usually comes from analyzing the data according to some group. So in this case, I've just chosen to group it by year. And you can see that in a fixed effect model, if you group by year, you still get unbiased predictions. So if you throw in a fixed effect for the year, then your predictions in that year will, on average, be correct. So it's not biased for every year. However, it might be biased for a different group. So here I show it's biased for property type. On average, it's not very close to 0. Now, a level of sophistication that you didn't have to go to, but you may have thought about, was how could I tell if it's significantly statistically biased? Well, you can do an ANOVA or a t-test using the mean and the standard deviation of the residuals to get a t-statistic. You don't have to do that, but I've got the code in the answer key online that I'll post the URL to at the end of this lecture. Okay? So all you had to do was show me somehow that the bias existed. If you were very, very enterprising, you might try and do that in a way that conclusively demonstrates it. But just showing me something like this is a sufficient answer to the question. Now we're going to move to the nonlinear part. So fit a generalized linear model that predicts whether a listing is a freehold using the price of the listing. So I've got some explainer text here that you might want to read if you were confused by this part. But the model itself is very simple. if you do the same thing I did for property type for local authority, you can do that. You'll see it. That happens because some local authorities are more expensive on average. So those places will get underpredicted by your model because it's lumping them all together. Same way that I got the rest of it. Anytime you're looking at bias for a group, get the residuals, do a group by, and get the mean of the residual in that group. It's conceptually the same pattern, no matter the group. I have to move a little quicker just to make sure that we can get through this. But I'm happy to show you that later if that's cool. So the actual model that I was asking you to fit looked like this. I'm not too happy that it's splitting the model over 2 lines, but it might look like that. So I was just looking for is freehold as your Y and your price as your X. The data should come from the sales data, and the binomial is at the end. Yep, Zoe, adding 1 is great. Indicates that you want the intercept, that's fine. That's super cool. Great. So everybody should have been able to do this at this point. According to the model, do more expensive listings tend to be freehold properties? So there's a couple ways you could do that. You could use predict and do it for a bunch of different prices. But the simplest way to do that is just to look at the effects. I need to estimate it. The simplest way to get this result is just to look at the effect. Price is positive. It's small because we're dealing with house prices, which are usually on the order of £100,000, but it's positive. That means that an additional an additional pound to the price of a house increases the log odds that it's a freehold by, 0.00001. That becomes important when, say, if you increase the price of a house by 10,000, which is generally speaking a very easy change to make because they're houses, the probability changes quite substantially. So keep in mind again that we're still dealing with linear regression and the x's have not been transformed. So this is in terms of raw price. So if you were able to get this result somehow, that's great. All that's required is that you look at the estimates from the model. Is log odds different to probability? Yes, it is. So as we talked about a couple of times in the lecture and in some of the labs, the probability is a value between 0 and 1 that tells you whether or not y is equal to 1. The odds is your probability divided by 1 minus your probability. The log odds is the logarithm of that odds. So yes, the log odds is different from probability. If you interpret this as saying increases in price increase the probability of a house being a freehold, that's accurate. That is true because this is positive. But it's not directly what the model says. The model just says it increases the log odds. Fortunately, increases to the log odds also mean that the probability increases. So it's okay to say the probability increases. But you need to keep in mind, this is about the log odds. To improve on this, you could use the predict function, as I've told you. So I've set up a scenario here, which is the price difference in moving from 100,000 to 200,000 pounds. And I'm making sure that this outcome is in terms of the probabilities rather than the log odds. So I'm putting type is equal to response. When I do that, I get the chance that a house selling for 100,000 pounds, you could, yep, cracker, totally, good. You could totally do that. So here I'm showing just 2 points in the possible sets of prices. And I'm showing that if I sold a house for 100,000 pounds, there would be a 71% chance that that's a freehold listing. If I were to sell it for 200,000, there would be a 74% chance that it's a freehold listing. So that would increase the probability of the listing being freehold by about 3%, or 3 percentage points to be precise. So you could have done that as well. You could have made a plot showing the increase in probability and interpreted that. That would be very, very good. So I'm just showing you this in order from sort of the simplest way that you could get the answer, as long as you interpret this correctly, to something slightly more sophisticated. And then, of course, if you go beyond this and you do that correctly, that's fine. Make a histogram of the predicted probability that a listing is freehold. Describe this histogram. Okay. So what I was looking for here was for you to get the predictions from your model using predict. So that was, the predicted probability that any listing in your data is a freehold. And that's just predict freehold model type equals response. If you make a histogram of that, it looks like this. Now, I like histograms with a lot of bins because they're easier to look at, but you can have a few bins, as long as it's a bin, more than one bin, because a histogram with one bin is just a box. So you have to give me at least 2 bins to get the right answer, but I don't think anybody would put 1 bin. Okay, so I'm looking for that. Those are the probabilities. Using table, build some confusion matrices. So you could have used something else. I'm just giving you a hint about how to make these confusion matrices, whatever you want to do. Oh, by the way, yeah, if you want to follow this yourself, I should have done this earlier. I assumed that you would do it. It's teaching GDS. That should be live. Sorry about that. What was the description of my histogram? So this is the predicted probability for every observation you have. You get that using the predict function. And then I am making a ggplot of that using geom histogram. So that's all I was looking for. What's the implication of the positive skew in the histogram? That means that our model tends to think that there's a lot of properties that are very probably freehold. And then there's a bulk of properties that are possibly maybe not freeholds. It isn't necessary for these predicted probabilities to be normal in this case. Just like it's not necessary for your predicted y to be normal in a linear regression. Only that your errors are normal. So in this case, the implication is that we have some properties, these up here especially, which the model is really certain are freeholds. And then we have other properties, the bulk of the distribution, which our model is kind of assigning a constant probability to. It's not quite sure. Okay? But that's what this distribution is showing. So I asked you to build some of these. And I've given you a little hint in the actual thing. That's where I used emoji. Georgia asks, the bulk is above 0.5, so does that mean there's always more of a chance than not that it's a freehold? Yep, it does. So I'm doing this way using the with function which allows me to use the column names directly. But you can do this however you want, and I'm not going to penalize you if you use X tabs or use a pivot. It's okay either way. However, what you may have found is that if we set our threshold to 0.5, as Georgia has just asked, this means that our model predicts all of the properties as freeholds. So you can see here that the predicted column only has one thing, and that's true. So this model has a bunch of true positives and a bunch of false positives, or sorry, a bunch of false negatives. No, a bunch of false positives. So it has a bunch of true positives and a bunch of false positives, and then no true negatives nor false negatives. The model never predicts false. If we go down to the next threshold, that's how I'm computing it, using the same pattern. I'm duplicating a lot of code here for the purposes of clarity so that you can see it, but it's not actually necessary to repeat these things. You could obviously just save your predictions and your residuals way up top and then just refer to them over and over again. That's fine. But as I suggested, the best way to do this is to make a column and refer to that column over and over again. And in the model where we set the threshold at 0.75, you can see that now we predict both falses and trues. That's because it's basically like, going back up to our histogram, I'm drawing a line, and in this case, I'm drawing a line right at 0.75, so something like geom v line, x equals 0.75. Oh. What? Geom v line x-intercept is equal to 0.75. Whatever. I don't want to waste time troubleshooting why that isn't working correctly. But it's like you're drawing a line at this 0.75 boundary and saying everything below it is false and everything above it is true. Okay, so it's like you're drawing a line vertically there, and everything above it is true, and everything below it is false. So our confusion matrix for the threshold of 0.75 has a bunch of false falses. Great, those are correct. Bunch of true trues, but now we have a really large set of false negatives, which are things that I predict are false, which are in fact true, as well as a smaller set of false positives, which are things that are false that I'm saying are true. Okay? Does everybody see that? This model probably has too high of a threshold because its false negatives are too large. Remember that increasing the threshold involves a trade-off between your true positives and your false negatives. So the last one, we have a really, really, really high threshold. This model only predicts 52 true positives. Its false negative rate is huge. This is way larger than that. So that false negative rate is almost 1. However, its true negative is pretty good. Most of the falses are predicted correctly. Only 3 of them are predicted as accidentally true. Okay, so that's generally the pattern when you increase the threshold, as we saw in the workbook. 3.5 of the contingency tables shown above, which gives the highest percentage of correctly classified observations. So here I'm doing this by writing my own function because I find this to be an easier way to do this, but you might not find it to be that easy, so that's okay if you did this in an alternative fashion. What I'm doing here is I'm taking the pattern of adding a column on and computing the table that I've done before, and then I'm getting the sum of the diagonal, and then I'm returning the percent, or I'm returning the count, depending on whether or not the percent argument is true. So I'll show you a manual example of that here in a second. So if I have a table, so let's do this. If I have a table, so I have a confusion matrix like that, and I just save that to a table. We'll call it TBL. That's my confusion matrix. The accuracy is the number of false falses and the number of true trues divided by all the cases. So using the diag function, I can get the diagonal here, the main diagonal of that confusion matrix. The sum of that is the number of correctly classified observations. If I wanted the percentage, I could do that divided by the total sum of the table. Okay, so I'm just writing the function as a way to minimize the amount of repetitive code that I have to write. I don't expect you to write that function, but it's a general kind of high-level description of this. Make the confusion matrix, get the sum over the diagonal, and divide, if you want, by the total number of cases. Patrick, I recommend checking the answer key code yourself online. It should be there if you can access that. But I will show you just because it's hard to see when all the stuff's like shuffled around. So I'm declaring a function called accuracy that takes a threshold, and whether or not I want percent, which I set to true by default, I'm going to use the sales data as my reference, and I'm going to use this freehold model as my model. If I provided different values to these, I could customize this function for different data or different models. But I'm just doing it this way so that I've kind of abstracted it a little bit. Then just like before, I'm creating a crosstab. With my data, I'm adding a column of predicted probabilities from predict model, type equals response. And then I'm computing a table where the actual is freehold and the predicted is the threshold. Well, predicted probability greater than threshold. So I'm just taking the things that I've done before and abstracting the input a little bit. Then I'm getting the sum of the diagonal of the cross tabulation. If you wanted to write that in pipe, I think it would be something like xt piped to diag piped to sum. Whichever one you think looks better, you can do. Then I'm returning the percent if my percent argument is true. If I've set this option to true, I'm returning the percent of things that I've classified right. Otherwise, I'm just returning the number that I got right. So that's all the function does. And as I showed you, all I'm expecting you to do is get the percent there. And you might have done that by, putting in 91282 plus 52 divided by blah, blah, blah. That's okay. It's not ideal, but that's okay. Yeah, it's okay. I understand. It's fine to just plug in the values, because once you have the confusion matrix, you can just see what the accuracy is by writing that out. That's okay. Absolutely fine. I haven't taught that code. I didn't say use the diag function to get the diag of a table. It's okay. It's fine. It's not a big deal. The point here again is to get that to get the answer. So it's okay. It's fine. Please don't worry. Yeah. So anyway, the other thing that something that you may be interested in. So I've asked you to compute a couple of thresholds, and this shows you the plot of the accuracy at a couple of different thresholds. So your accuracy remains constant until you actually hit the distribution. Your accuracy shoots up and then declines slowly as the threshold increases to 1. So the best point for your accuracy is somewhere at the peak of this mountain, with a threshold somewhere slightly below 0.7, according to the accuracy. But you didn't have to do this either. I just wanted to show you how that works. The challenge question should use plot rock to make a rock curve. And if I recall correctly, that should be done using gemrock. Yep. Right. So ggplot. I would have to look this up off the top of my head. I think I might have left this out. I think it's, yeah, I'm not gonna, I'll post the answer to the challenge in a second. I'll work on it. It should take me like half a second. I just can't remember it off the top of my head. I don't want to fumble around while we've got to still talk about the last section. Okay, so the very last point is section 4. Go back to your analyses in part 1.4. What percentage of the other house types are freehold or leasehold? Is there an issue with confounding in your model from section 3? Yeah, there is. You can see for yourself. Whether or not a property is freehold basically boils down to whether a property is a flat. So if you look at the table of freehold and leasehold, so here I'm grouping by the property type and getting the percentage of flats that are freehold. Because the is freehold is a binary variable, the mean is the percentage of ones. We've done that early on in the course. We've done that in spatial modeling too. It's okay to justify this in a different way, but this is how I'm done it in the answer key. So if you're a flat, you only have a 2% chance of being a freehold. If you're a detached house, you have a 98% chance of being a freehold. So it's really not about price. Both expensive and inexpensive houses still are freeholds. Whereas flats, no matter how expensive they are unlikely to be freeholds. So there's a confounding variable here, which is the property type. If we include that in our model, our conclusions change. So this model, let's, yeah, we'll just fit it with the fixed. So this model looks like this. We have property type plus price. And I think online I might have used a -1 to remove the intercept. That's okay. But basically, I'm looking for including property type and price in the model. Okay? So you can see from the effects that the probability of being freehold is way higher for detached. Semi-detached is slightly less. Terraced is even less likely. But for a flat, it's strongly negative. So this reflects the table of percentages above in 4.1. Then also, when I throw in the property type, I get a small negative association between price and whether or not a flat is a freehold. So my price effect changes sign, and it also becomes statistically insignificant. So this is an issue of confounding. It's not about price, it's about the property type for whether or not it is a freehold. That's the last answer. You just have to fit the GLM with the price and property type. Yeah, it's enough to identify that that whether or not, yeah, I'm just looking for property type. You don't have to say whether or not it's a flat. Yeah, it's totally okay to do that type of model, but then you need to be careful that the contrast that you're measuring there is the detached house. So it still is the case that the price effect is going to be the same in both models. So it's not too big of a deal. But if you interpret the property type variable and you use a contrast model, you need to be able to express that correctly. So that's all. Great. Those are the answers, guys. Well, guys and gals, I want to be inclusive, and anybody else. That's it. I hope it wasn't too hard. At the end of the day, it's only, I think, 20 lines of code. So, like I told you, this isn't a coding class. From here on out, I'm much more interested in you getting the right answer than I am, you know, how you get there. So yeah, it's aside from my kind of dalliances with the functions, you know, the answer key should be very straightforward and contain things only that you've seen before. Most of the time, it's just the most confusing thing might be doing your group bys. So are there any kind of high-level questions here before we proceed? Because now it's for you to do the to do, you know, whatever you want to do from here on out. We're moving to the next chunk, basically. So anybody have any questions? You will see that in the multi-level modeling part for the next chunk, you will have to do a multi-level logistic regression. So this stuff won't go away, but you'll just need to be able to interpret what that means. So the next component is going to use some slightly different data. It's going to focus on respondents to a survey about earnings and demographics rather than house prices, because I try and vary it up. So yeah, my suggestion is you get on the reading, because then on Monday we'll talk a little bit about the actual theory of multi-level modeling, which shares a very substantial component of that for the logistic regression. So that's all I got to say. I'm going to quit the recording, and I'm not seeing any questions popping up in the chat. So Noah says, can you ask about the date of the final assignment? You can, but I can't give you any answers yet. It hasn't been confirmed. I need to get with the office about that. What? Okay, Isabel, thanks for letting me know. It was my impression that these were booked out for the Haggett, but maybe something has changed. I see. I was informed that this was, I see, okay. I understand. No, it's okay, it's not your fault. The reason is because we've changed the Friday time. So in theory, you could attend in the Haggett on 4 o'clock, but since we had to reschedule the Friday lab, you might not be able to use it on Fridays. So I'll talk to Matt, it's fine. It's cool. Anyway, I'm going to stop.